Great, a good morning to you. My name is Ian Rowlands. I'm a professor here in the Faculty of Environment and also the Acting Executive Director of WISE, the Waterloo Institute for Sustainable Energy, and delighted by your attendance this morning. Very appreciative that you've been willing to come out and spend some time with us on Energy Day. One of WISE's key goals is to foster collaboration, foster connections between different parts of the university and also different parts of the university with our broader community as well. So as I was having conversations during the break with various people, be they students talking about the research posters, be they community members talking about the initiatives going on, be they faculty members talking about their grand plans for research, I see lots of wonderful opportunities for continued collaboration and very, very proud to be playing a small part in trying to catalyze that and foster that. And delighted that you're here with us for our second panel of the day as well, which is entitled The Future of Energy Service Delivery. And our moderator is going to be Dr. Steve Young. And Steve is an associate professor in the School of Environment, Enterprise, and Development here at the University of Waterloo. And his research investigates sustainable materials management, life cycle assessment, and enterprise carbon management. And amongst his activities outside of the walls of the university, he serves as the vice chair of the Canadian Standards Association's Group Technical Committee on Environment. And Steve earned a PhD in materials, metallurgy, and materials science from the University of Toronto. Steve, delighted that you agreed to accept our invitation to moderate the panel. It's all yours.
Thank you, Ian. I've been looking forward to this day to see this information come together, to see this collection of people. We're talking now about the future. And the focus is on how energy systems are being transformed. We're looking at transformations that we see in terms of organizations, the types of organizations, but also the types of technologies that are shifting from things like big monopolies and grids to smaller distributed systems. Our panel consists of 3 professors from 3 different faculties here at the University of Waterloo, and they have been asked to put their minds to what this future might look like and what we can do about it. Specifically, I have asked them to address 4 questions. How do you want energy services to be delivered in the future? What is the biggest catalyst for facilitating that vision? What is the biggest barrier in realizing that vision? And what one thing could people in this room be doing to help catalyze that and move that forward? So our first speaker is a professor in geography and environmental management. And in my School of Environment, Enterprise, and Development, he focuses his research on building sustainable communities by creating win-win opportunities for the environment and the economy. He is particularly concerned about how local economic development strategies can achieve a sustainable future with a key interest in sustainable energy systems. He serves on the board of directors for REAP, Green Solutions, locally. Professor Paul Parker is a PhD in economic geography from the London School of Economics and Political Science. I will hand it over to Paul.
Thank you, Steve and Ian, and especially thank you for the first panelists that were here. Test, it's where we always start. We're at the university. How many want their future to be the same as the past? Oh, good. We were looking for change. Thank you, because that actually becomes my major barrier at the end. The biggest problem of not changing is we just want to keep doing what we are currently doing. So to look 50 years into the future, I want that to be different. I want it to be substantially different. I want to set aggressive targets, but practical and achievable ones. How much? 2050, 80% reduction in our carbon emissions. We need to get back to a globally equitable level. Can we do that? Let's start with the history lesson. Before we go to the future, historically we said more people want a bigger economy, using more energy, and that creates more carbon emissions. This has been the trajectory of success for the last century. That's what we want into the future, right? Wrong. We want to change the equation. We want to say, yes, we can have people living comfortably, but we can do it without the carbon. Where can we break the equation? They say, oh, the Europeans are, or the Danes are. But then North Americans always say, but that's somehow different. So I say, okay, we can't do what the Europeans do. Okay, there may be some reason for that. The sun might shine differently or something. I don't quite understand. But can we look in North America then? Is it possible in North America to break this stranglehold that we have? And where might we see? We have this 1990 base level under the IPCC agreements. So who is growing their economy, growing their population, and cutting their emissions? Canadian example number one, Vancouver. Vancouver grew the population by 27%, grew the jobs by 18%, yet cut their emissions to actually be below 1990 levels. Well, wait a minute. That kind of sounds like a growing city, and it's possible now. How do they do that? They do it by passing progressive rules in the city. All of their buildings have better building code requirements. At their new standard for 2020, all buildings will be net zero. In other words, you're going to produce as much as you consume in the big picture. Set the rules. The industry says, yes, we can deliver. Oh, you mean it's possible in Canada? Have to think about that. Well, then what are they looking at for the future? Their answer is also 80% reduction. Can we get there? My suggestion is, this is the 21st century. We don't need to use the 20th century equation. So how are we going to do that? In community energy planning, we like to talk about three important fundamental principles. Number one is managing your demand. So it's the conservation, it's the energy efficiency, it's the investment at the starting point. We build systems for a long period of time. We build buildings to last 50 years. We need to think about what the impact is going to be over the next 50 years. So that's where we'll turn to my colleague here. John will tell us we need to have a much better building envelope. Add the insulation. Make sure that it's airtight. Solve the problems, and guess what? You have a much lower demand. With lower demand, we can then turn to our renewable sources. We suddenly say, well, there are many renewable sources we can draw from, but who is winning the race? Ian gave us the example this morning of how popular solar is. The growing demand for solar means it's going to become integrated into all of our building decisions. We have on-site sources. Also, what's that rule number one? If we're going to get away from carbon, we've got to get rid of putting the carbon devices in. No one needs a furnace. Pardon? It's cold in Canada. No one needs a furnace. If we actually think about having that high-performance shell, we don't need the gas line or the oil tank. And if you don't invest in that technology, we have radical places like where? Nova Scotia, where they say the oil tank is too expensive. Well, how do you heat your house in the cold of the winter? It's the mini split heat pump. It can actually go both ways, both for your heating and for your cooling. Oh, we're not burning oil and gas, we're using electrons now. So what we need is a clean source of electricity. Change the debate. If you want to reduce your carbon emissions, stop using the carbon fuels. We can do it in our buildings. What, can we do it in our transport, though? We love our cars. We're not going to give up our cars. So again, I say, oh, okay, I know we can't give up our cars. But again, Vancouver's example, over the decade, you had a 180% increase in bicycle traffic. Whoa, trips, people walking, using their legs, 44% up. Transit up 50%. And so in this growing dynamic city, how are the gasoline sales going? Down 7%. Oh. Cars coming into the city, down 10%. Oh, you mean there's actually less gridlock, more people getting around more easily. Well, this is sounding a bit radical. Canadians getting out of their cars. Oh, but sorry, I live in Waterloo. I couldn't possibly do that. So where do I want us to go, Steve? Action for everybody in this room. We are facing an election. Are we having energy and environmental issues as core issues in this debate? We should. Because this isn't brave new territory. Waterloo, we should be willing to go to brave new territory. We can learn from our friends. LRT is a big debate, but all I hear is sort of, well, is it really going to be faster? Is it really going to cost that much or not? Well, what about the energy and environmental consequences? My message, learn from the success stories. I love Calgary. What? Calgary, the oil capital? Calgary sold their light rail system by saying, ride the wind. What does that mean? It means I'm not putting gas in my car to drive to work. Instead, I'm taking an electric rail into work. And how is that powered? Their secret was 12 turbines out by the foothills of the Rocky Mountains. So let's get that straight. I can actually reduce my carbon emissions by not driving my car up King Street, but instead by taking an electric-powered rail system that's powered by 12 turbines on the Bruce or some other appropriate wind location. Oh, so if I reduce my emissions, I go to renewable sources, and then I add, appropriate mechanisms like buying wind-generated electricity from strong wind sources. Gee, using these new smart grid technologies to balance the supply and demand, I think we can have a different future. I think we should all vote for people that have that vision that says 80% reduction in our carbon by 2050 while allowing us to grow as an innovative and leading community. I believe we can do that. Thank you.
Thank you, Paul. Very inspiring. I'm going to move right on. Our second speaker on this panel is an associate professor in the School of Architecture and the Department of Civil and Environmental Engineering. His research investigates energy efficient, healthy, durable, and sustainable building designs, often supported with advanced computer simulation, lab testing, and full-scale performance monitoring. He's also a principal in Building Science Laboratories, Building Science Consulting, Inc., where he consults to building product manufacturers, government agencies, and a range of design professionals and building owners. He received a PhD in civil engineering from the University of Waterloo. I give you Professor John Straub.
I'm afraid my presentation won't be quite as rousing as the previous one, but then that would hardly be possible. One of the challenges I think I constantly am faced with in my work at the university is that there's the buzzword of we need to be innovative, we need new, we have to go onward and upward, and the problem is that, but a lot of us already know the answers and no one's listening. And I heard a bit of that in what you said. And so, when I got the questions from Steve about the clicker technology, you maybe hit the space bar, it'll go to the next one. Oh no, it's locked up. Should have brought my own laptop. All right. Right. All right. We're good. So I actually wanted to change the question a little bit as opposed to why, what would I like the energy delivery to be? And the first thing is, let's stop focusing on wind turbines and PV panels and ground source heat pumps and wind power, et cetera, because actually most of the energy we produce in Canada and all developed worlds is wasted. What percentage? It depends how you look at waste, but in the order of 3/4 to 90%. And depending, as I said, how you look at it, in all the high-rise buildings we're building in Kitchener-Waterloo right now, they all have emergency exit stairwells. Those stairwells have lighting in them that runs 24 hours a day, 7 days a week with no one inside that stairwell. That's actually not counted in waste, even though the stairwell's lit and no one's there except, I don't know, maybe a crack dealer or something once in a while. But if you try and get switches so that when someone walks into the stairwell and the light turns on, the city will say you can't do that because it's unsafe. Just as an example of some of the things that we have to deal with. So reducing, it's a mindset change of not just we need change, because that is absolutely step number one. If you want a different outcome, you're going to have to change what we're doing. We also have to say that it's not just always about the stuff that you can see, and this is a huge problem. Now, many people like to say, look at the wind turbine, except for some neighbors, and many people want to put PV or those little baby wind turbines on buildings that do absolutely nothing except like Conestoga Mall. They look good, but they don't actually do anything. It's a total waste of resources. And that's because people want to see something. They don't actually focus on what matters and what works. And so we don't have to invest a lot. Where we need to invest is this second level that was introduced, is that we have to change to a more symbiotic relationship between producers and consumers. And that's meaning the smart grid type technology. And a lot of the technology will happen when regulations get out of the way. Because right now, of course, it takes a lot of paperwork for me to try and join the FIT program for getting PVs. Even if I want to put photovoltaics and pay the full shot and get zero money from the provincial government, it will cost me thousands of dollars and hundreds of hours to be allowed to put photovoltaics on the roof of my house, totally paid for by myself. So do I need innovation and technology? I don't think it's what we need is innovation and technology. This is a relatively old chart about carbon emission abatement, which again, Paul mentioned a lot. It's not just energy. We're mostly worried about energy because of resource depletion and the carbon emissions. So this was something done by McKinsey Associates, a well-known management consulting firm to big corporations. And they looked at what does it cost to reduce a ton of carbon emissions. There's a whole range of technologies across here, things like solar, things like HVAC, heating and equipment efficiency and all that. All of these things cost money to reduce carbon emissions. Everything on the left side of the chart here are things that if you were to do them, they would reduce carbon emissions and save you money. They are equal amounts, there's actually slightly larger amounts of opportunities to save money and cut carbon emissions as there are to spend money and save carbon emissions. So the problem, again, isn't that we don't have technology, as Paul has mentioned. It's like, you know, insulation's a pretty good thing in a cold climate, and doesn't have to be reinvented. We have fantastic products and systems available. Lots of people willing to do it. What we don't have is consumers willing to spend the money to save money or regulations to force people to do the right thing. They will force you to wear a seatbelt. They will not force you to insulate, even though both of them have obvious, well-proven benefits. So I don't need to invent anything. We have the toolkits to go most of the way. 80% by 2050, we have all the tools and equipment we need to do that, and almost every bit of it really is affordable and will not increase costs over a life cycle of any investment. If I want to go beyond 80% by 2050, yeah, we have to do some stuff. But guess what? The good news is we got like 30 years to come up with that new stuff, to get to 90%, 95%. But 80%, we know how to do it, and in fact, it can be done at essentially no cost. So what catalyst do we need? I don't know. I've been looking for 15, 20 years. I don't know. People say, oh, energy's got to get more expensive. Doesn't matter. Go to Europe where they spend 25 cents a kilowatt hour on electricity, and you see people with lights on. Fewer, but still tons. And by the way, in the wonder of Danish power, 50% comes from coal, just to be quite clear. So it depends how you, yeah, they got a lot of wind turbines, that's great, but 50% is coal. And the percentage of coal in Germany is rising, just FYI. So what we need is, I don't know, I kind of am at a loss here. I think it's partly awareness. I figure if you knew this, it would help. The other thing that seems to work is just not having power. So when the power goes out, well, people start paying attention to, geez, maybe it would be better to be more efficient. So what are the barriers to this? Well, it goes back to awareness. The opposite of awareness is ignorance. People don't know that it makes sense. The building code is the worst possible building you can build without going to jail. It is not what customers should be asking for. But customers don't know that. Customers go in and they buy granite countertops, floor-to-ceiling windows so that they don't have no place in their condos to change their underwear, as far as I can tell. And they don't know that that's a bad decision because they think the government has protected them, right? They got a code. And the culture is also a problem. The people who build the buildings have zero incentive to make buildings that are energy efficient. The people who build cars have zero incentive because they don't pay for it. GE, who makes your dishwasher, gets nothing out of making an efficient one. So there's a problem, it's called the agency problem, of connecting the people who pay for it to the people who make it. And that's a fundamental disconnect. And just price signals, historically, simply haven't worked, which is why there are massive opportunities to save energy, reduce carbon, be healthier, and be more comfortable, and save money. But they're not being done. And so cranking up the price is probably not going to do it. What can people do? I don't know, just invest more in reducing waste. We call that efficiency because it sounds nicer. But it's basically waste, right? If you buy a gallon of gasoline and you drive to work in an F-150, you're wasting 98% of that gas. Or you could ask for a more efficient pickup truck, right? So the new EcoBoost is like, look, it only wastes 96.5% of the gasoline. That's good, right? It's still 96.5%. So when we think about the whole energy equation, it's stop wasting is often the easiest, the cheapest, the most available, but it requires a mindset shift. And then we have to worry about increasing supply, but actually, if we were to get to that 80% number, which many people talk about, we already will have that supply in no time at all. We were almost at the required renewable energy supply today and will within 5 years. What we have to do is stop the waste, stop the bleeding. That's it.
Thank you, John. Some stimulating ideas in there. Our next speaker from another faculty again is a professor and the Cisco chair in Smart Grid at the Sheraton School of Computer Science, the Faculty of Math. He co-directs the Information Systems and Science for Energy Lab, which aims to use information systems and sciences to increase the efficiency and reduce carbon footprint of energy systems. He is an ACM Fellow and author of 2 graduate-level textbooks in computer networking. He received a PhD in computer science from the University of California, Berkeley. I give you Professor Keshoff.
Thank you very much. Thank you. I'm going to try and follow 2 very difficult acts. All right, so these were the questions we had. What is the biggest catalyst for the vision? What's the biggest barrier? And what's one thing people in this room can do? And we've heard from both my predecessors about something that you can do, which is mindset change, or policy change, regulations, right? Mindset and policy. I'm going to propose something which is the opposite. I'm going to say something which you may not want to believe, but I'm going to say it anyway, and I'm going to contradict both of them, not because I disagree with them, because I think there's more to it than meets the eye. What I propose is the biggest catalyst for change will be the bean counters, the accountants, okay? Cost is king. So basically, when you want to see any kind of change, it comes from 2 things. It comes from technology, the availability of technology, and that technology gets wrapped up in policy, regulations, you know. To give an example of this, when policy in Germany changed and they said, we're going to allow you to get a lot of money, we're putting in solar panels, 2008, suddenly solar panels sprouted from everywhere. I was in Germany a couple of months ago, and they have about 10 million, I don't know how many millions of panels, entire hillsides covered with panels. That is the power of policy. But the power of policy is meaningless without having the technology to back it up. You need to be able to have the technology before the policy makes it. So you need both, right? Okay, so, but the cost king, the king of cost right now is solar. Look at this. This is a solar farm in Germany. This is, I don't know, a few 100,000 panels, and this is not the only one. You have really hillsides covered with panels. That comes from the combination of technology and policy. So the question to ask is there technology and is there policy already in place? And here's what the answer looks like. This is a chart from the Rocky Mountain Institute in Boulder, Colorado. And what it shows on the x-axis is time, that's 2010. It's projected out very conveniently to 2050, just the right time frame. So when I got this question to answer, I was Googling around and I found just the right chart. But look what's going on. On the y-axis is the cost in dollars per watt in 2009 constant dollars. And so what it's basically showing you is for different technologies, what does the cost look like 50, in 20, 50, 40 years out? Okay, so the bottom line is this one over here, the yellow line. The yellow line right now is about $4 a watt. That's the install cost per watt, rather than the actual silicon only costs about 75 cents. But look, it's going way down. It's going down actually to just about gas combined cycle, below onshore wind, below coal, below hydro, below nuclear, below everything, right? So what does this mean? The way I interpret this is that if the accountants rule the world, and unfortunately they do, in 2050 they're going to choose solar, just because it's the cheapest thing out there. That's really all there is to it, right? The question that Paul asked is, why is it that you don't put solar on your roof? Well, because it's onerous, because it's expensive, because you don't know if you're going to be in the house 7 years from now, and then what are you going to do? But guess what? There's a large number of people out there, including all the people who spoke in the first panel, whose business will suffer if you don't put solar. So they're going to do the lobbying and the policy change and the regulation to make it possible for them to make lots of money, right? And this is basically a free market solution, okay? So what I believe is going to happen is this cost curve over here is going to drive everything else, okay? We're going to get to this situation in, we may replace the, the ski slopes, right? With this, okay? So you may need to drive further out to do your skiing because we're going to replace that with this. And that just happens because this is where the money is, right? So what about the policy? I believe that the policy work has been done. The policy work that needed to be done was to get solar down to sort of the competitive range over here, $4, instead of being up at $40, it's off the screen, that it was. What happened in Germany was to put in the enormous amount of money that is required for solar to be competitive. Now that China has got into the game is over. We're going to be on this 38% reduction in costs per year for the next, I don't know how many years. And so Germany has paid a big price for this. My answer to them is, thank you, Germany. It's really true. They've saved the world, okay? So what is the barrier? The barrier, I think, is storage, okay? And what I'm showing over here is sort of this is from the IEA. Again, it's a technology map for the future. It's actually projecting out to 2050. What would happen if you had, so on this side over here is the gigawatts of storage that are needed in each country. So in China and India, European Union and United States, which are sort of the four big consumers of, together these account for about 5 billion people. So everybody else is in the noise. Okay, so if you have these four, it's all that much. So 2011, this is the amount of storage available. It's not much. Okay, in fact, basically zero over here and a certain small amount of storage over here. And what this is 2DS is the 2 degrees increase in temperature scenario. Business as usual, you want to cap it to 2 degrees, and then you want to have breakthrough, and then you have EV adoption. So 2DS, you get quite a bit of more storage because we want to do this. But look at this. This is breakthrough. It says if you have a breakthrough, you're going to get huge amounts of storage deployed, and that's where money is being spent already. So there's about $120 billion worth of investments in storage technologies that's underway today. Okay? Because every single advance has the potential to not only have storage for the grid, but for cell phones, and for electronics, and for your car. So if you can crack the lithium-ion puzzle, and you have the 5% increase in everybody else, you get billions and billions of dollars. That's why Elon Musk is investing in Gigafactory. Okay? So I'm not a chemist, but if I were a chemist, I'd be studying lithium-ion. And all the chemists around here are pretty damn smart. So they're all doing this too. And the winner who gets down to the price curve is going to be taking home a lot of money. So I believe these breakthroughs are going to happen. Okay, I believe that this is potential. So once you've got that, you're basically done. You have solar, you have storage, you have everything you need. The mindset will change because this is driving everything. cost drives everything. So my summary is, everything Paul said, I completely believe in. You know, we have the technologies available, we should use them. Everything John said is also true. We waste a lot of energy. We should try to reduce the cost of energy. But I think the other point I want to take is, even if we don't reduce energy use, the first chart that Ian showed in the beginning with the solar taking off and providing all of the world's energy is going to come true. So that leaves me with one last thought, and then probably we should take questions. And that is, what does it mean to us as a society, and what does it mean to me as a researcher to have these things change? What this means is that suddenly we have a source of energy which is variable. The clouds pass over the sun, and suddenly your energy drops from 100% down to 5%, okay? And at night, for some weird reason, there is no solar energy production, okay? So what do we do with this? Integrating solar into the existing energy system is very complicated, and it turns out to be twofold. One is, how do you deal with variability? And the second thing is, how do you put storage at just the right places and just the right amounts so that you don't spend too much money on storage and still get all the benefits of available and energy needed when it's energy available when it's needed, like at night. And it turns out that these two questions are extremely similar to problems that arise in the internet. In the internet, we have variable streams called videos. So you download videos from the YouTube. It's the same as downloading electrons from a solar panel. And in the internet, we have these things called routers, which have buffers which store packets. It looks a lot like batteries. And so my research group and my work has been to take those ideas and innovations that you discovered in the internet and apply them to this decentralized solar system with storage. And it's a beautiful fit. So we're finding lots of interesting problems to work on, but also at the same time try to make this a reality. So that's basically what we're doing over here. So thank you for your attention.
Well, thank you, Keshav. I'm going to ask the three speakers to sit at the front, and I will join them. We've moved from municipalities to building fire exits to thanking Germany. But I have some questions. I'm sure there's some questions from the audience. I will repeat the questions for the benefit of the microphone. And then if you can, direct it to one of the individuals, and we'll have a chat from here. We've got a good half an hour.
Don't all speak at once.
Yes, there's a question in the green shirt here, please. Okay, I'll repeat the question. Thank you. I think this is to John. And the question concerns waste energy, and have we really made any advance here in Canada on this issue of wasted energy?
And I think the question was more locally, although because Toronto, Waterloo, Kitchener, Guelph, really the area that I can speak most informed about is the building sector, which incidentally consumes about 40% of the energy that we use in Ontario. And we basically are a little bit better than the national average and a little bit worse than the best attempts, which happen to be in British Columbia and Vancouver. But I guess my point on the economic side was that while we are better, and many people who have a new home actually don't pay very much money, which is they pay more. If you buy a latte from Starbucks every time you go to work, you spend more money than you do on energy in a modern house built to the Ontario Building Code. The average Canadian spends more money on internet and telephone services than they do on heating their home if they bought their house that was built in the last 2 code cycles. So the average person doesn't notice that when you add up those multi-million dollars of consumers, that it actually is a lot of energy. And economically speaking, it would make sense for them to spend $3,000 more on their home to be able to save $450 a year on energy. But they don't know it, and the regulations don't require it. And the builders, of course, build what the worst they can get away with, because that's the competitive market. So are we doing better? We're doing a little better. Are we doing what we should be? Not even close.
May I add a radical idea? Finally, we finally in 2013 got the R2000, which was supposed to be the standard for the year 2000, introduced. So our new houses, especially single detached, are improved. But it was great last night to hear that finally in the Ontario Building Code, and in Toronto, the glass towers will be illegal from next year. With 2015, they're doing a radical thing. They're bringing in a standard of you actually have to have less than 170 kilowatt hours per year consumption per square meter. So you can't just build and consume as much as you like. There's a standard being introduced, and hopefully in the future, it will get even better. But the result of the standard means you have to insulate your walls in Canada. Radical concept, but it should mean that we get beyond glass and actually have insulation coming.
I think I want to just to mention on why that's so important. People often say, are we meeting the code or beating the code when it comes to buildings? But it's actually irrelevant, because the code is not a fixed number. Depending on how you interpret the code and how you enforce the code, the outcomes are radically different. Like the buildings that we've built on campus lately, most of them are crap. And all of them meet the code or even meet LEED. And yet from an energy consumption number, they're horrible. So the fundamental, and I think breakthrough, is that they're actually going to tell you 170, a number. And the beauty of the number is that people can get the energy consumption. And there's a whole team of people in Ontario who every month go out there and read meters, write the number down and send it to you. So that number is easily available. And now you can see, do I have a building that meets the code or not? That's going to be profound, because people are going to be held to account, not just to say, I'm building a LEED building, I'm being green in one way. No, it'll be a number that you can say, well, is it true or isn't it?
There you go. There's a question in the front here.
Yep. So you mentioned part,
So I think the question is to Paul, and it concerns meeting the IPC targets, and are we getting there?
Excellent question, and here I have to confess I'm the old guy. Are we getting there? If you look recently at what our governments and countries have been doing, no, we're not. We are actually improving in efficiency, so the government can say we are more efficient. We do actually make a small gain every year. We get an extra 1 or 2%, but that's not enough because our growth is so much, so we're not turning it. What actually scared us enough to take action was the oil crisis of the 1970s. So we really need to be talking about a 4% reduction a year, so 2% covers our growth, and then we're actually getting a substantial, a real gain. So we need to double our savings efforts. Can we do it? Of course. We've done it before. John has all of the answers that we need here now. We add in Keshev's technology. It's a done deal with things we already know. Are we implementing it now? No. Could we? Absolutely.
On this side.
Yeah, so one of the things you guys mainly talked about at the barrier was policy and how policy influences the different energy systems we have in Canada. As engineers or as technical people, what can we do to help influence policy to get on the track that we want to get going?
So the question concerns how we can address the policy problem that all three speakers, I think, have highlighted. And Keshav, do you want to take a go at this, or?
I think I can speak from your side, which is how can we influence policy from the side, from the technical side? The answer is, I wish I knew the answer. Okay. In some sense, we have a disconnect between those people who do policy and those people who do technology, and it's quite evident from the fact that, I, as a technologist, we try our best to get the message out, but there has to be, at some level, a receptive audience, right? And so the position I'm taking here is that at some point, money talks and policy gets made, right? And the money talks here will be the people who are going to benefit from solar. But there probably is a better way of doing things. I don't know how Vancouver achieved, for example, these policy and regulation breakthroughs, so maybe Paul can tell us about that.
Well, the short answer there was politics, if people agree. My initial answer to you in terms of if you make it close to what people are currently doing, so like on the problem of our windows, you know, if this magical nanotech insulating membrane can revolutionize our windows, that would be pretty easy because we've got lots of window companies that would be, they're used to different coatings now, so if they have a new magic coating, that would be easy because it fits with what they're currently doing. Making me do something a little bit different, that's where this is my biggest barrier is just status quo. Let me do what I did last year and carry on. So the answer is if your new technology is similar to my old technology, so it's easily incorporated, that's an easy one to get new advocates. Bringing on new players means we have to fight harder. It's possible, but it just is harder. Whereas if you can bring the current industry on side to say that's a winning technology, it's going to be an easier road, would be my first guess. The Vancouver answer, I think, was really political. Of people said environment counts, and then they said, oh, we have the technical answers, so let's put in bicycle lanes on some roads.
I would, you asked as an engineer, and while the technology, making what Paul said makes perfect sense to me, it's also that we as engineers need to be more involved in society. It's not, we can't just sit in our rooms and do stuff or write blogs to each other. We need to actually be willing to go and speak to the city councils and the local planning commission. We need to be able to talk to our neighbors about, in an explicable way, no diffie cues. And I think that's part of the challenge that we as a face is that we do need to communicate better about what we know, because if you can explain it, actually a lot of people will give you credit for, well, okay, I guess that's the science, they'll listen. But we don't do enough effort as a profession, as an engineering community. We talk about whiz-bang that no one can understand, but we need to talk about stuff in ways that people can talk about. And I don't think politics comes to me after culture. I think what was different in BC, like in California, another super energy efficient economy, is it's the culture came first that they gave a shit. That's the technical term, but there's, So first they cared, then politics, the process kicked in to say, what do we do about it? And then you actually get a change. Right now, I just don't think enough people care enough about it. I think that's largely because they don't know enough about it. I can't understand how rational beings could know what many people in this room know and think it's okay to keep going. So I think, first we have to get some awareness, and then I think the culture will shift. And that is what's in Germany, there's more people who cared, and they're less scared of talking to engineers, because there is some. So when you put that, that's a pretty potent mix. And the same sort of thing happens in California, that startup capital, all those Elon Musk type geeks, is that they're not scared about the technology, and they have a culture of caring about the environment because they've managed to destroy a lot. So they get to, it's like the Germans, right? You ruin a lot, you're going, hey, Canada has the problem that we have so much natural environment that, what's a few thousand miles in northern Alberta? But slowly we're going to, even that's going to run out, or even that's going to encroach upon us.
There was another question in the front here.
Yeah, sorry to keep dwelling on policy, but I think, John, in his presentation, you said that, at least in building codes with regard to solar, policy needs to get out of the way. And then the next slide, you said that sometimes you need to force people to do what's good for them, seatbelts and insulation, and policy came up in the 3 talks. So we've got good policy and bad policy. I know it's a difficult question and pretty big. How do you tell the difference between good policy and bad policy?
Okay, that's a nice, concise question. Thank you. How do you tell the difference between good policy and bad policy?
Well, I would say this applies to all walks of policy, and it's like, does the policy encourage the desired outcome, or does it discourage the desired outcome? Now, in this room, the desired outcome is a lower carbon, lower resource-intensive future. And so if we were to use that as a measure, well, I guess it becomes pretty easy. You can argue at the margins about whether this policy helps a lot or a little, but a policy that makes it difficult for a person to buy solar panels, install them on the roof, and connect it to their house electric system, I don't know how you see that's good policy in terms of meeting the outcomes. What it is it's policy intended to protect the people who have invested assets. It's intended to make sure the status quo stays the status quo for as long as possible. This is the big challenge about the cost. Even when PV is significantly cheaper than, as an example, go to the Caribbean. There's literally tens of millions of people paying top dollar for electricity that's generated by unreliable diesel generators in a sun-drenched country, where PV today is cheaper by far to purchase and operate. But there are policies, there are cultures, and there are vested interests to keep it going. And that's why they don't. So this is going beyond the policy question itself, but it's like, does it have the desired outcome? That's, I would say, is how I would assess good policy.
Do you want to add?
If I can add the important two differences. One is exactly starting with John's point of saying, what is your goal? If your primary goal is reducing carbon emissions, set the carbon target. So that's why I like the idea of the energy standard being in units. And then you have flexibility in how you achieve it, as opposed to what I was going to say, not to label it as bad, but otherwise we come to you as the advisor to say what is the best way to get there, and relying on one person's pathway. So I would argue options for more flexible pathways allow for more experimentation to say we can get to your target, and it might be that somebody else comes up with a better way that I had, as opposed to me saying, thou shalt do it by having, a solar panel of X dimension. If you just say, make sure this house is, a net zero, how are you going to produce it? The answer is simple. Industry will respond. You go to Japan, the big builders there, their cost of installing solar on the roof, they say, is zero. Why? Because it's built-in solar from the start. I've got to put a panel on the roof anyway. Instead of putting normal roofing, it's a solar roofing. Wiring the house anyway. Let the industry solve it. Set the target. You want this to be a net zero building, they'll find ways to make it.
If I could add something there, I think the other issue is that the policymakers need to be technologically informed, right? Part of the issue is that the policymakers are sometimes operating without knowing the state of the art or the projections of what can be achieved, in 10 years, 20 years from now. Certainly, the PV industry, if you did all your projections with $10 a watt or $20 a watt as it was even 5 years ago, you would not be able to make a policy that said you must produce 20% of electricity from PV overall in this province, right? You would not do that because you didn't have the projection, you didn't think about it. So we don't know, for example, what EV technology is going to be, but we could have a projection that's technologically well informed that says storage is going to be $100 a kilowatt hour, therefore EVs are going to be at this price point, so we should have a policy of 20% of the University of Waterloo fleet be electric vehicles by 2020, right? It's a perfectly reasonable thing to do as a policy without specifying the details, but that has to be technologically well informed. And that's the interface between the technologist and the policymaker, which is not that good right now.
In the far back. So the question concerns the cost curve and how accurate that would be in the future in reality.
So first of all, I should say that cost curve comes from Rocky Mountain Institute, so give credit where credit is due. The second part actually is, let me give you a thought example to explain where this cost curve comes from and what it makes sense or not. Imagine you're paying 10 cents a kilowatt hour for grid electricity, right? Which is In fact, you'd be paying for peak price right now. It just went up on November 1st. It's going to be it's going to be 14 cents a kilowatt hour in Ontario, right? Now, if I can say to you the following, put PV on your roof, and you're going to be paying effectively over the 20-year lifespan 7 cents a kilowatt hour, or during the sun, when the sun shines, which is effectively also your peak time, right? Now you're going to say, okay, good, I got the grid. Whenever I want to, I use the PV for my own use. I don't need storage. I'm just cutting my electricity bill by just putting something on my roof, right? Do you agree it's a good idea to do it or not? Totally agree. So the cost curve so this cost curve, as I understand it, does not include storage. It's just the cost, levelized cost of PV usage on a sort of per watt basis, assuming that that's what it costs. So what I'm saying is that the reason I'm saying the accountants will drive it is because if your cost of solar on levelized basis over the lifetime of the energy produced is 20 years, is less than the cost of grid electricity, you're going to go install solar anyhow with no storage. Just use it when the sun is shining. And that's why in Canada, the #1 producer of solar energy it's not a green company, it's Walmart, because they're cheap. They're not green, they're cheap.
They're not green, they're cheap. Which brings the next question. Well, let me rephrase that as a question. Do you see that the price expectations, the cost expectations of PV have actually come down more rapidly than was originally anticipated?
I believe so. I mean, Ian is the expert here, so I can scarcely contradict him. But my belief here is that PV at the end of it is a silicon technology, something that we had a lot of experience with in the electronics world. And by repurposing it, by using less pure silicon, which is what PV is, you're kind of bringing together this enormous embedded base of knowledge on how to produce silicon and get the volumes up and deploy it. Right now, the cost of PV is not in silicon anymore. Actually, it's in the metal, the structures that you need to put up. Right? You need to worry about wind loads. And you need to worry about the fact that if you put a PV panel on your roof and it's tilted, it's like a big sail. So if a windstorm comes, it's going to rip your roof off.
And the snow fence.
And the snow fence. So, I mean, those are the practical problems that push PV from 70 cents to $4.50 install cost per watt. That innovation would come from perhaps the civil engineers to figure out how to get integrated modular systems. So that you can install. So, I mean,
well, I appreciate that you've just said that the material scientists have done very well.
They have. The architects and the civil engineers need to get their game.
Get on with it, yeah.
There's another hand over here. We've got another 5 minutes, so we can squeeze 2 more in, maybe.
Just going over the same question of technology and policy coming together. I think that the notification and address these issues when the technologists we are so focused on part of the details and we leave out other sectors. For example, in California, I was there in the CPU in the regulator a couple of months ago, and they were telling we will be happy to foster more and more solar and microgrids, but we have the issue, for example, with the security, with the safety. Because if there's if one of the feeders gets disconnected and we have to send a crew, what happens with that solar panel that you're producing? And then the union says we will not fix that feeder. Stuff like that, I think that's part of the reason why many of the universities around the world are moving into these more multidisciplinary approaches. but there's a fixed cost to the grid if you're connected there. So I think that technology and policy have to go together in that way. But we also, as technologists, we have to broaden these views about how the grid works. And remember that along with the computer or the electrical, there's other engineering things that have to match, and also the social and economic parts. And I think that that's where we fail. I don't know if you can comment.
So I will repeat, both John and Keshav are nodding their heads. The question concerns how you're connecting these new technologies that are emerging and moving forward to the grid, and there's a policy interface there.
Okay, let me first answer the first part about for example, energizing the grid because so let me just give you a story. So I met this president of Canadian Solar, I guess, at the time, and he visited my lab. He said, "Firemen hate us." And I said, "Why do firemen hate you?" They said, "Well, they go off to the building and they turn off the mains, and then they get a shock because the solar is still on, right? And so they hate us." And that's a valid point, right? You don't want the fire people, I guess, to be hurt because of solar. So that points to what I call experience with technology, right? So the first installations, yes, there are going to be problems, but if there's a large enough base, hopefully these kinds of things are figured out, and you say, okay, whenever there's a fire alarm, we turn off the solar. Just as an example of the kind of things that need to be done.
Play on their pride by saying, how come German and Japanese firemen can handle this and you can't?
So I think the introduction of any new technology into a society, there are all sorts of unintended consequences, and the whole point is to find them and fix them as soon as we can. And that's what technologies are good at, and that's our job, that's what we do, right? The second part of it is saying, how do we as technologists interact? So I'm going to put in a plug for WISE here. So Ian, you should take note here. So WISE is a great organization in this university, right? It brings together people from completely different areas to talk to each other in ways they've never done before. So for example, I get to talk to Paul, who's actually in a completely different faculty. If it weren't for WISE, I would never talk to him or to Ian. I get to talk to people in electrical engineering, right? And in chemistry and so on. So we have in WISE a forum at this university which is, I believe, fairly unique. I haven't seen it any other university in the world. And I think it's a great opportunity for us as participants in WISE and in this university to make use of this resource.
And just to add to some of those comments, most of the examples you used and we were using are actually not something that are going to be solved by a civil engineer talking to an electrical engineer. They won't even be, frankly, identified. You have to actually go out in the real world. You'd need to speak to firemen, and you'd need to speak to architects, and you'd need to speak to building code officials and all those people, right? And actually, I think that's where we don't, Waterloo is one of the better universities at that, but we still don't do a very good job. I mean, I routinely, it's a problem that I spend too much time talking to industry. I mean, from an academic point of view, this is a big problem of mine that I speak to real people. And because that doesn't result in a peer-reviewed paper, right? It's not innovative to speak to the people who are running the power grid. That's not innovative, doesn't result in a peer-reviewed paper. That's not a good use of my time, is it?
Excellent. I'm going to interject right here. I've heard some excellent quotable quotes. Riding the wind, voting, getting beyond the stuff that we can see. We don't have very wise consumers, that we could be replacing ski slopes with PV panels, that engineers should get more involved in communications and politics, or that the politicians should get more technically informed. I'm going to thank the panelists.
They're not green, they're cheap. I thought that was the best.
Oh.
They're not green, they're cheap.
I wasn't keeping up. They're not green, they're cheap. I'm going to thank the panelists very much, and I'm going to hand it over to Ian to wind up this session.
Thank you. Great. Thanks very much. Please join me in thanking our panelists. Fantastic, and I'll just say a couple of quick words here, and I'd like to thank the members of both panels today. I think we've been given lots of wonderful information, lots of great ideas, and lots of quotable quotes as well to take forward. And I'd like to thank the WISE team for their hard work in putting today on, Joanne, Iris, and Lily. And I'd like to thank all of you for engaging in this conversation and discussion about these critical issues that we're facing. We've been given a wonderful foundation for thinking about the way in which technology interfaces with society to advance solutions. We've had a lot of discussion here about policy, engagement with people. I think the comment was real people as well, so those are very important people as well. And I very much encourage you to continue those conversations that may have been started today or may have been catalyzed today as well. And if you registered for the event today, we will reach out to you early next week with a brief survey, and we would love to continue to keep in touch with you as WISE. We'd love to get your feedback on what you thought was useful for you today, on what might be useful in a future incarnation of Energy Day, and how you might be able to be energized by more interaction with us in the future as well. So I'll wrap it up there for now and say once again to all of you, thank you very much for coming out. Enjoy the rest of the day.